Geometry was probably the first mathematics people did. What happened was human beings were trying to manipulate the world. And number counting things was great, but being able to figure out how to build something if these were your reference points in reality. And so a lot of early geometry deals with points and lines and the shapes that come up. Now we're in chapter 10 in the book, and I'm not going to go through all of the point line geometry. There's just some basics that and I don't mean basics like, oh, this is so easy you need to know it, or you should know it on that. What I mean basics is they're things that build into other concepts. And one is that, let me draw this properly. The early geometry was all points and lines and circles and how those relate. And so the basic idea is that the two shapes, the circle and the line, have a common relationship. If I work all my way all the way around a circle, I start here and I rotate all the way around. Let's say if I had some fixed point here and I rotated this all the way around, we say that's a 360 degrees. So we start at 0 degrees and going all the way around the circle is 360 degrees. So halfway is 180 degrees. So what ends up happening is we say, hey, a line has an angle of 180 degrees. So if I cut a line with a shape, whatever angle is here and whatever angle is here, they have to add up to 180 degrees. Now there was a really nice line that people liked, which is if I divide my circle into fourths, pretend I did this properly. I'm doing this freehand here, so I'm a little crooked. These are called right angles, and they're 90 degrees. And right angles gave some special things. Squares have right angles, and right angles were very useful in building things. If I wanted to construct something at a right angle, all the weight is straight down. It's more sturdy. If I construct something at a slight angle, this weight has no support on it. And that's why this angle was considered special to early peoples, because they were trying to build and construct better things, and they found different ways of constructing them. They also found that if you were building a structure and you built upwards, the weight got very strong here, and it would start to collapse. And so they would, as height would go up, they would gradiate things so that their main support was there. And this is why we have pyramids. And if you hollow these out, right, there's support issues coming through. And so they were playing with how weight and space manifested itself. And so we see a lot of geometry comes along angle, and how angle manifests itself back to a circle. And a lot of emphasis around a triangle. And I guess the big thing that comes out of a right triangle, which is fundamental to almost all mathematics, this pops its way up in all mathematics, is if I have a right triangle, the two legs of the right triangle, if I square their sides, they equal the square of the hypotenuse, which is the hypotenuse, which is the long side that's opposite the right angle. And that's triangle geometry. We'll look at some triangle geometry, but what I want to focus on is a lot of the rules that come out of this knowledge. They're the things that we tend to use more. We don't go back and redo a lot of points and lines. We tend to use the Pythagorean theorem. without proving it, or without coming back to it. So I'm just going to talk about shape in general, and some of the things we get from shapes. So we tend to talk about things called polygons, which are many-sided. And so if I want to enclose a shape completely, I need 3 sides. Right? If I just have 2 sides, I get a line. And so polygons get named by the number of sides they have. Well, in this case, this actually is getting named by the number of angles it has, because it's a triangle, because it creates 3 angles. And what we're going to do is we're going to look at polygons, and then we're going to look at regular polygons, where the sides are all the same. And what we're going to want to do is figure some things out about them. So, I'm trying to get back there. A regular triangle, so this is a triangle, a regular triangle would have all sides of equal length. So make one freehandish here. So that would be a regular polygon. And as a triangle goes, it would be an equilateral triangle. And so regular polygons, whoops, I'm still on the line drawing tool. Regular polygons, I'll just put regular poly. Sides are equal length. Sides of equal length. And so triangle 3. And then in our next polygon is a quadrilateral. Quad for 4. And so that's a quadrilateral. It has 4 sides. And this one's a square. It doesn't have to be a square. We can have other regular polygons, and we'll look at their naming conventions. And then we start, quad is 4, pent is 5, so we get a pentagon, and then a hexagon, and then a heptagon, and then an octagon. Right, your stop sign is an octagon. Let's see here, how do you do a pentagon? That's supposed to be a pentagon, right? It's not regular, but it is a pentagon. And then in a hexagon, oops, a hexagon over here. Again, I'm not doing as regular as I should here, but that's a hexagon. 6 sides. And a heptagon, 7 sides. And I'm going to skip drawing a heptagon, and I'm going to go to an octagon, which is 8 sides. And we're using Greek numbering systems here, the quad, pent, hec. And let's do my octagon. I hope you see that's would be a stop sign if I didn't like miss over here. Octagon, which is 8 sides. And so the name and the number of sides. And so poly, side, many side. And then once we get to the 5 sides, 6 sides, 8 sides. The first part tells you how many sides. Quad is 4, but lateral, we're talking about the opposition. And triangles, there's a big focus on the angle. And so the names developed from those. What I'm going to do here is let's see if I can. Give me 2 seconds here. Nope. Trying to switch screens here. Give me 1 second. I think. There we go. And so here are the type of quadrilaterals. Don't want to have to draw all of this out. A parallelogram, all the sides are parallel to each other. So if I were to continue these through, they would never intersect. And so we show parallel by putting a dash. And so the dashes here means that this is parallel to this, and this is parallel to this, which means that their opposite angles will be of the exact same size. A rhombus is a parallelogram that the sides are equal length. A rectangle is a parallelogram with right angles. Not equal length, but right angles. And a square is a rectangle with equal length and right angles. And so a square is a rectangular rhombus, which is a parallelogram. It would match the definition of all of these. And a rectangle would match a parallelogram, and a rhombus is a special type of parallelogram. And then we have a trapezoid with one set of parallel sides. And trapezoids are actually very important in building. And so trapezoids come up mathematically a lot. So do squares, right? We've already been using squares to build areas. Sorry for my funky drawings here, but figured we'd get to a good place. Well, what we've been doing then, and we'll continue this, is we've been working on the concept of area. And so we've been taking the ability to measure something in squares, and we would say that there is some length and width. And if it's a rectangular solid, if these are right angles, we could say that the area of a rectangle is the length times the width. And we can figure out what the area is. We can also figure out how far we have to walk around the edges, or how much fencing we would need. So the area was length times width. The perimeter, well, if I walk this, it's the length, and then I walk a width, then I walk the length again, and I walk the width again. If I put fence down, I have to cover the length twice and the width twice. And so the perimeter, how much stuff I need to go around the edge, and the area have these formulas for a rectangle. And that's really what we're going to work on. The nice thing about polygons is that, to figure out the perimeter, you add up the sides. So a regular octagon, let's see if I can draw a regular octagon. And say I want to put reflective material around the edge of a stop sign. And I know the length of one of the sides, and to figure out how much reflective material I need to get how much little reflective tape I need to put around. So if that's a side, all of these have the same side because it's a regular polygon. Please, I know I drew that side a little off, right? There's 8 sides, so the perimeter would be 8 times the side. And so if I could measure this, and let's say it's 16 inches, then I would need 8 times 16 inches. 8 times 6 is what, 48? Let's see, 8 times 7, yeah, 48. Carry my 4. I'd need 128 inches of reflective tape, and then I'd lay it down, and I'd have my sides. And I'd get the reflective tape off. Right? And so that's the usefulness of perimeter, is that it figures out how much we need to go around the edges of things. A neat thing that came out of polygons is that the angle measure add up to a consistent thing. So in a triangle, all the angles add up to 180 degrees. In a square, all the angles add up to 360 degrees. And so if we extend this idea, what we can do is we can take the number of sides minus 2 times 180. Let's try that. 3 minus 2 is 1 times 180, that's 180. 4 minus 2 is 2 times 180, that's 360. So the angles all have to add up to some measure to fill in this. So a triangle has 3 sides, so the angles add up to 180. Square has 4 sides, so the angles add up to 360. A pentagon has 5 sides, so n minus 2 is 3, and 3 times 180 is 0, 4, 540 degrees. And so we know how the angles add up. We're starting to figure out how we can manipulate these things. And that manipulation is what helps us fill space or predict what we need from things. So we have the area of a square. Let's give an area of a triangle. And the area of a triangle is 1/2 the base times the height. But it's finding the base that's interesting on a triangle. So let me get my triangle drawn here. And I can pick any side to be the base. We usually put the bottom, because remember how I said people like to talk about these as construction. And if I drop down from the angle at the top to the bottom and I make a right angle, that's my base, or my height. Sorry, my height. And the base is what that connects to down here. And so what we're doing is we're saying if I were to cut this triangle out and put it over here, it would fill out a rectangular solid. And what we can say then is this length helps determine 1/2 base times height. And so our area of a triangle is 1/2 base times height. Notice how in this one I've cut my base in half and I've made a square over here. And this works out for all triangles, even if it's shaped oddly. Let me this triangle here, I drop that down as my height, and that's the base. This still has an area of 1/2 base times height for the triangle. And so that helps us get the area of a triangle. Well, let me switch over to here. That helps us get the area of a parallelogram. Because if we look at a parallelogram, we can see that there's a triangle here. If I take this triangle and I put it over here, I've completed the rectangle. And that gives me a base times height for a parallelogram. And so we can add to our angle formulas that the area of a parallelogram is base times height. And I guess this is the hardest part about geometry, is trying to remember what the areas for all these figures were. I usually have a list of them looking through, but normally I will use a rectangle, which is base times height. And when I have a shape like this, I'll look to see if I can cut something off and make that rectangle. And I'll also look for triangles because I remember the triangle is 1/2 base times height. Everything from there, then, I tend to, either look up a reference sheet or I try to make rectangles or triangles out of the things I have. Oops. Let's go out one. There we go. And that means, let me look here. And another thing we could, so we're going to build up a collection. Sorry, choppy sound here. Sorry about that. We're going to build up a collection of areas we can use. I'm going to add one more here. It's a trapezoid. Now, if I cut this trapezoid, I get the same height. But I get two different triangles. I get a triangle with a long base and a triangle with a short base. So I have 1/2 h times a plus 1/2 h times b. If I put them together, I get this 1/2 h a plus b. And so we're building up I got really loud there. Sorry about that. We're building up a collection of things we can use to calculate the area. And remember, area is how much paint I need to cover a surface. At least if we want to think of it as like some type of analogy. Well, what comes into play now is the shape that I told you we danced around, which was the circle. And so a circle has two ways of talking about things on it. We can talk about the radius, which is from the center out, or we can talk about the diameter, which is from edge to edge passing through the center. And so the center measures out, and this is the radius, and this is the diameter. Now, this comes into, it's easy to make a circle with a radius. If I fix one edge of something down, and I rotate it around, it will trace out the circle. And so radius is used to construct a circle. But if I go to measure a circle, I have to find the middle to find the radius, and that's hard to do. But if I were to take like a vise or something that I could measure the outside edges, right, if I put it between two pinchers, like a vise, they would spell out a diameter across their length. And so diameters are easy to measure. And that's why you'll hear us talk about circles both ways. We'll talk about the diameter and the radius. And so what we can say is the circumference, or how much stuff is around the edge of a circle, is 2 pi times the radius, or pi times the diameter. And pi times the diameter tends to be the way we talk sometimes. In fact, the Greeks used this as how they measured angles. They didn't use degrees, they used pi's to measure angles. And there's a thing called radians. And so if I were to walk halfway across the circle, or I would make a diameter, we would say 180 degrees. The Greeks would say they want pi radians. And the area of the circle, then, is pi times the radius squared, or pi times the diameter divided by 2. Because notice, the diameter is 2 radii. So if I want the radius, I take the diameter and divide it by 2 squared. But if I square that, I get d squared over 4. And so these become the formula that we get to use for our friends, the circle. Alright, and these are some useful geometric things that we can use for area. And in the last video, we're going to look at volumes.